International Dark Sky Week and the Day of Light. In this talk, Michelle Edwards, Associate Director of Kitt Peak National Observatory, is going to explain us how optics and photonics is used in other branches of physics, like observational astrophysics. First of all, I would like to thank Michelle for accepting this talk today. We know that you have a strict schedule, so thank you for spending your time with us. Also, I would like to thank the whole roster of Photonets UV for their support, and especially Martina, our advisor. Dr. Michelle Edwards is the Associate Director of Kitt Peak National Observatory, where she coordinates and oversees the operation of over 20 telescopes on the Kitt Peak summit, just outside Tucson, Arizona. For 10 years prior, Dr. Edwards worked at the twin 8.4 meters Large Binocular Telescope Observatory, also in Arizona, where she managed a team of observers as scientists and worked to commission and operate bleeding-edge cameras and facilities. As a Gemini Observatory Science Postdoctoral Fellow, she acted as project lead during the commissioning of a special near-infrared imager for use with Gemini's state-of-art adaptive optics system. During her 3 years in La Serena, Chile, she executed more than 100 nights of observing and nighttime commissioning of new instrumentation. Dr. Edwards earned her PhD in astronomy for the University of Florida. Her thesis work included extensive involvement with the Canarias Infrared Camera Experiment, CIRCE, a near-infrared instrument for the 10.4-meter Gran Telescope de Canarias in La Palma. Now I give the floor to Michelle, and I am sure that everyone will enjoy the talk. Thank you.
Thank you so much for that introduction. I hope that everyone can still hear me. And thank you also to Martina for the invitation. So I am Dr. Michelle Edwards, and as was said, I am the Associate Director of Kitt Peak National Observatory, and today I'm going to talk to you about what it's like to work for the world's largest observatories. Before I begin, I would like to offer a land acknowledgement for 2 of the observatories that I will be speaking about today. Kitt Peak National Observatory and the Large Binocular Telescope Observatory sit on the original homelands of the Tohono O'odham people and the San Carlos Apache tribe, respectively. Both peoples have stewarded their lands since time immemorial. So astronomy is a very visually beautiful science, and it's natural whenever the field is mentioned to think about the most extreme and exciting results in images, things like black holes represented here, or exoplanets, which are planets that are found around stars other than our sun, or planetary nebulae, which are the evolutionary endpoints of stars much like our sun, or distant galaxies, gigantic structures that contain dust, gas, and billions of stars. Some of them are even colliding with each other, forming elaborate and spectacular objects like the antenna galaxy that are pictured here, in feats that we refer to as galactic cannibalism. However, what is rarely discussed or considered are the technologies that are used to create these images and make these amazing discoveries. And since I have worked for 2 of the world's largest observatories, that's Gemini Observatory and the Large Binocular Telescope Observatory, and built an instrument for the third, which is the Gran Telescopio Canarias, and I am now the Associate Director for Kitt Peak, which is a mountaintop with almost 20 telescopes and a number of groundbreaking instruments, I thought it would be interesting to focus on the technical advances that make our science possible. So we'll start today with a definition of astronomy, starting very simple, and we'll discuss the scale of the research that we do. And you'll see what I mean about that in just a minute. Then we'll talk about why large ground-based telescopes are necessary, and we'll describe the tools that we use in our astronomical research. We'll move on to some of the more difficult challenges that we encounter and talk about the technologies that we use to address these issues and challenges. Okay, so this image that you see here looks fairly nondescript, looks fairly unamazing. There's no large galaxies or really exciting planets or black holes, it appears in this image. But really, this is an incredibly special image, and it tells us a lot about the scale of the challenges we face in this field. This is the Hubble Ultra Deep Field, This was an image that was taken by the Hubble Space Telescope. The story of this image: astronomers pointed the Hubble telescope to an area of sky that they thought was mostly blank, an area that they thought did not host a lot of clusters of galaxies, an area without many visible stars. And they allowed the Hubble Space Telescope to integrate for 1 million seconds. So we took a 1 million second exposure. Now that sounds like a long exposure, but for Hubble science, this is actually not atypical. What they found when they took that exposure, this image, was a surprise. In this single field, almost every single point of light that you see is an entire galaxy, each of those galaxies containing billions of stars. For some example, the Milky Way galaxy, our own galaxy, has about 400 billion stars. Okay, so clearly this image is not a blank piece of sky. All of these dots and points of lights are galaxies. But what really, really is stunning is that this is really 1/13 millionth of the total area of the sky. And that number is very hard to understand, but if you were to take your arm and hold it out at the night sky and put up your thumb, this image would only cover 1/50th. Your thumb would only cover 1/50th of this image. So we have in this one image 10,000 galaxies, hundreds of billions of stars, and yet it is just 1/50th of your thumb on the night sky. And that gives you an idea of just the sheer challenge and number of objects that astronomers are trying to learn. The other part of this image that's absolutely striking is that it is not just a two-dimensional image or really a three-dimensional image, it is also a four-dimensional image. Many of these objects are billions of light years away, which means that it took billions of years for the light to reach us, which means we are actually looking back in history. So there is one object here, this very small, faint object with this very boring name, UDFY 381-35539. Astronomers not always so great at naming objects, but this object is 13.1 billion light years away, which means when this light arrived to Earth, we were actually seeing this object as it was 13 billion years ago. And that is only about 300 million years since the Big Bang. So really we're seeing the very earliest origins of our universe in this tiny little dot. So what we realize is that astronomy is the study of all matter and all energy in existence and its evolution over 14 billion years. It is an immense four-dimensional laboratory. Okay, unlike many of our sister sciences, one of our main challenges, unlike chemistry, biology, geology, and even physics, is that we cannot directly interact with what we want to study. The stars are merely too far away. And that means that we have to use some very interesting tools, the most important of which is radiation. The electromagnetic spectrum is basically the astronomer's toolkit. So we are lucky that astronomical objects emit radiation across the entire electromagnetic spectrum, from the radio to the gamma ray. Unfortunately for us astronomers, but fortunately for all of humanity, there are parts of the electromagnetic spectrum that do not penetrate the Earth. These include the ultraviolet, the X-ray, and the gamma ray. And again, this is good for us because it's allowed for the development of life as we know it on Earth, but bad in that we can't see astronomical objects from the ground in these wavelength regimes. So we have built, over the last 30 years, great telescopes that can see in these wavelength ranges so that we get the entire puzzle, the entire electromagnetic spectrum, which is, again, really one of our only ways to study our astronomical objects. However, today in this talk, we're going to focus on mostly the radiation that does penetrate the Earth's atmosphere, and that is the infrared and visible. And of course, there are space telescopes like Hubble and the new JWST that also look in these wavelength regimes, but because it penetrates the ground, we are able to use ground-based telescopes, and that is what the focus of this talk will be. Okay, so before we begin talking about these telescopes, I want to talk a little bit about some light collection basics. So if light is our only way to study these objects, or one of our only ways to study these objects, the amount of light that we gather becomes incredibly important as it's our only tool. So how do we gather the most light that we can from these astronomical objects as the light penetrates our atmosphere? Well, what we want to do is have a large light gathering power. And the way I explain this, it's sort of like if you were to go outside during a rainstorm and you had a very small bucket, you would not collect very much rain. If you go outside with a much wider bucket, in the same amount of time, you would collect a lot more rain. Well, the light that's coming from the stars and other astronomical objects is very similar to rain, and our telescopes are basically our buckets. So our light gathering power, it turns out, is actually just a ratio of our two apertures. So if we had those two buckets, one small and one large, our light gathering power would be the ratio of those areas, which basically would be the square of the radius. So we were given one amazing astronomical telescope or instrument, our eye. And so if you were to think about your eye as a light collecting bucket, the size of the radius of that bucket would be about 4 millimeters. So if we compare that to a telescope that is there with you, this is the telescope T50 telescope at the Universidad de Valencia. And so if you were to compare that telescope, which is about 51 centimeters or 255 millimeters in radius, then you would see that just this modest telescope there in Valencia at the Observatorio de Aras de los Olmos actually gives you almost 4,000 times the light gathering power of your eye. So compared to some, and the reason that we, again, care about this, as you gather more light, you are able to see objects that are intrinsically fainter. So these are objects that simply output less radiation. And you are also able to see objects that are more distant. And these more distant objects may be faint or may be bright, but they are far enough away that by the time their light reaches us, they look very faint. So I wanted to talk a little bit about some of the telescopes I've used and the light gathering power that it gives us over our human eye. And so the first is a telescope here at Kitt Peak National Observatory, the 4-meter Male telescope. And that gives us about 250,000 times the light gathering power of our eye. The Gemini telescope in La Serena, Chile, which gives 1,000,000 times the light gathering power. And the 10.4 meter Gran Telescopio Canarias in La Palma on the Canary Islands, which gives us 1,690,000 times the light gathering power of our human eye. Okay, so one of the other tools of astronomy that's become obviously very important is how we actually collect that light. So I think that many people in the public believe that astronomers are still sitting behind our telescopes looking into an eyepiece and recording what we see. And I put this here as kind of a very interesting piece of history. So Percival Lowell is an extremely famous astronomer who built Lowell Observatory in Flagstaff, Arizona, which is where Pluto was discovered. And Percival Lowell was actually a well-regarded astronomer in his time, building really fantastic observatories and telescopes. But Percival Lowell was absolutely convinced as he looked through the eyepiece of his 24-inch Clark refracting telescope that he saw canals on Mars. And he spent thousands of hours at that eyepiece drawing these complicated maps of Mars. And he was convinced that there were Martians. And this was the not crazy held scientific view that there could be canals made by Martians on Mars in the late 1800s. So this gives you an idea that when you are simply looking through a scope and doing hand-drawn images, you can have serious scientific errors. And clearly astronomers have moved on from this. And what they now have, and this is powered by rapid advances in solid-state physics, are state-of-the-art detectors that are in special cryogenic, large-format instruments and cameras that record digital instruments. So here I show two large cameras. One is Circe on the GTC in the Canary Islands. And you can see this is obviously bigger than a person, almost the size of a small closet. There is another instrument shown here, GMOS at Gemini South. The next generation of instruments for the extremely large telescopes, 30 meters, that are being built will be the size of rooms. So instruments can cost between $10 to $40+ million, and they may take between 5 to 20 years from design to installation on the telescope. And they are not off the shelf. They are built and tested at major research institutes, usually by multi-person teams, and they are almost always one of a kind. They are often multimoded, meaning they perform both imaging and spectroscopy. Spectroscopy is an important tool in the astronomer's toolkit, basically by taking light and separating into its spectrum and looking for signatures in that spectrum, we can tell the age and composition of astronomical objects. So more than just an image, this tells us the physics that is powering the object. So it is a very important tool. And many of the spectrometers that we currently have don't just look at one object on a time. They can literally take the spectra of thousands of objects in a single image. So I thought it would be fun to, especially since this is an optics society, to talk a little bit about what the optical design for one of the large multi-million-dollar instruments might look like. And so to do that, I want to introduce you to the Canarias Infrared Camera Experiment, or CIRCE. CIRCE is a near-infrared visitor instrument for the 10.4 Gran Telescopio Canarias. It was built at the University of Florida. It does imaging and, again, spectroscopy. It has, and this is for the true optics nerds out there, an all-reflective aspheric optical design that fed a special near-infrared detector. And the reason I wanted to talk about CIRCE, especially given the fact that many of you are undergraduates or early graduate school, from what I understand, is to show you what some of the horizons could be for possible PhD or postdoc-like projects in the field of astronomy involving optics. CIRCE was the topic of my PhD thesis. I worked on the optical design, the optical tolerancing, the optomechanical layout, and the cryomechanical design of the filter wheels. So this gives you an idea of what CIRCE looked like. This is actually a model, a mathematical representation of what the surfaces of the reflective surfaces appeared. And so this was actually done in Code 5. Okay, just very quickly again, for those very interested in optics, what you're seeing here is the entrance window of the telescopes. This allowed light into the instrument. Then you have two folding mirrors that are, of course, unpowered. You have two collimating mirrors. So here you can see that the light is well collimated, which is where it would have passed through a pupil stop and some filter wheels. And then you have the real business end of this, which is this aspheric camera that does all the hard work to get us to this focal plane. And so again, this was done in Code 5, transferred into ZMAX, and toleranced in both sets of software. But this kind of gives you, again, a mathematical representation of these surfaces. This is what the real mirrors look like in real life. And so these are the actual optomechanically designed mirrors and the brackets on a bench. And you can really see and get a sense for the size of scale of these optics. So this optic in the very front here is where the telescope light would enter the instrument. This is the first fold mirror. And you'll notice that this is nearly the size of a human head, which means that putting your head in the back of an eyepiece for a telescope like the GTC is just very obviously impractical. Okay, so then I thought I would talk to you a bit about what it's like to work at a world-class observatory. And as I said, I have had the pleasure to work at 3 Gemini South Telescope in La Serena, Chile, which is where I did my postdoctoral fellowship, the Large Binocular Telescope Observatory in Tucson, Arizona, where I stayed for 10 years, and now Kitt Peak National Observatory, where I am the associate director. So one of the most fun parts of working in a big observatory is that you're really there to solve these interesting challenges to produce the absolute best science. And I wanted to talk about one of the challenges that we face and one of the ways that we solve it. But to do that, we need to talk a little bit about resolution and resolving power. So resolving power is the ability of an optical instrument to separate faraway objects that are close together into individual images. So what you'll see here, if you go from bottom to top, you'll notice that in the bottom image, this looks like a single star. And as the resolving power increases, and the angular resolution decreases, our ability to separate that blob into 2 stars improves. So larger telescopes have a smaller angular resolution. And again, smaller angular resolution is better. It means better resolving power. So this equation here, theta equals lambda over 1.22 d, is probably one of the most important equations in all of telescopes and astronomy. And what this tells us is the angular resolution decreases as the diameter of your telescope increases. So not only do large telescopes benefit you in their light gathering power, they also benefit you in being able to separate out stars that would appear close together, and now you can see them as two stars. So, okay, we build large telescopes, we have a large diameter, and our problem is solved. We have better resolution. Not quite. It turns out that it's far more complicated. There's turbulence in the Earth's atmosphere that distorts the light from the stars. So here we see light entering the Earth's atmosphere as a plane wavefront. It hits an inhomogeneous medium, which is the Earth's atmosphere, and you end up with a perturbed wavefront. What this means is that point sources like stars appear actually in our images as disks with angular sizes of about 0.4 to 1 arc second, and that's an angular measurement. At the best sites, that's at the best sites. At other sites, it could be greater than 1 arc second, up to 5 arc seconds or more. And so basically, your inability to distinguish individual objects is lost. The problem is that apertures larger than 10 to 20 centimeters basically see about the same resolution. So you have a 10 centimeter telescope and you have a 10 meter telescope, and basically, because of the seeing, you could see potentially the same thing in terms of resolution. So how do we fix this? Well, if we could just simply flatten out that wavefront that is hitting the Earth's atmosphere, or the wavefront that's being deformed by the Earth's atmosphere, if we could flatten out that wavefront and then basically observe it, we would gain back the power of our large telescopes and gain back our resolving power. And so we actually developed a technology to do this called adaptive optics. So we are able to use special wavefront sensors to measure those aberrations in the wavefront. And then we are able to use deformable mirrors to basically fix the wavefront. This is actually done as an iterative process. So the wave comes in, the aberrated wavefront is detected by the wavefront center. There's a correction sent to the deformable mirror. The light comes in, it's measured by the wavefront center, adjustments are made to the deformable mirror, and this is often called, in adaptive optics, closing the loop. And I just have a movie here to show you, it's a real movie, of what it looks like when you have an image and then you turn an adaptive optics system on. So here you can see the stars are quite blobby, and as the system comes on and the loop closes, you'll notice it's a real difference in what you can see. And this is very powerful because when individual objects, and I'll play that movie again, oops. If you cannot detect the light from individual objects and you cannot measure their spectra, then you cannot know anything physical about those objects. You only know about the group. So this is a really powerful way that's really revolutionized a lot of astronomy. Okay, so again, we think we've solved our problem. Unfortunately, it's not that simple. The wavefront sensors that we currently have, the technology, you need a very bright star to do this, to be able to sense the wavefront and fix it with the deformable mirror. And it turns out that over the entire sky, there's maybe only 1 to 5% of stars that are bright enough, which really limits where on the sky you can look and where you can use this technology. So then astronomers thought, well, what if we could just make our own bright stars? And so that's exactly what they did. We've actually developed what we call laser guide stars, which are special high-powered sodium lasers that we aim into the Earth's atmosphere. They basically excite the sodium layer there, and they produce a bright star that we can then use for our special wavefront sensors. Okay, so we figured out about turbulence. We built bigger telescopes. Now we built lasers for those telescopes. The problem must be solved. Well, it turns out not so simple either. When you have these lasers, when you only have one laser, really the atmosphere is very complicated. There's many layers in the atmosphere. And when you have one laser and one deformable mirror, you're really only able to correct for one layer of the atmosphere. And what that means is, of course, you have a volume of atmosphere. As you move away from the laser on the image, you start to notice what we call the cone effect. There's an elongation of the star. So you actually have an image that would be diffraction limited and beautiful, and it's distorted. And it's distorted by the fact that as you move away from the laser, you're sampling a slightly different part of the atmosphere. So you're basically missing data outside of the cone, which causes the degradation of the wavefront. And this occurs only about 20 arc seconds away, which is a very small field of view of the sky. Again, it gives you some idea that the 20 arc seconds is a lot smaller than just the diameter of the moon in the sky. So the solution to this is a complicated system called a technology that's called multi-conjugate adaptive optics. And that already sounds like a fairly complicated word, but really all we're doing is aiming more than one telescope at the sky using more than one deformable mirror. And by doing this, we're able to understand all the different layers of turbulence. And that builds a three-dimensional volume model of the turbulence in the sky, which allows for a better correction over a larger distance. So one of the people who was the forefront of this technology, one of the observatories, was Gemini South Observatory in La Serena, Chile, where I was a postdoctoral fellow, and I worked on a system that was called GEMS. Again, it was a multi-conjugate adaptive opter system that had 5 lasers. These were fairly high-powered lasers, and basically it was able to deliver this diffraction-limited image, so the image that the telescope should be able to deliver to us. It was able to correct the turbulence over 1 arc-minute field, which was very large compared to anything at the time. I actually worked with GSOI, which was a specially designed camera that took the input from this system. So some neat pictures here. Here you'll see the 5 laser beacon, so that's this image here, and you can see it makes its own little constellation on the sky. This is a really neat image that I took at Gemini South during one night of commissioning, and an image of the instrument that was, again, used to capture the digital image. So as the scientist in charge of the special near-infrared camera, I actually worked with over 20 people or more on the entire team to commission, to basically get this instrument up and running. It was over 50 nights, and it was really an honor to be a part of this really dynamic and amazing team with some of the best experts in the field. And so this is just a quick image of what it looked like when we did that correction. You'll see in the bottom of this, the seeing limited image, so that's what the stars would look like with no AO correction. Classical AO, which is just that one laser correcting 1 layer of turbulence in the atmosphere, and then GEMS, which was able to correct multiple layers of turbulence. 3 layers actually, with 3 deformable mirrors. And this is a representation of the entire field of view, and you can see how even and beautiful and resolved all of these stars look. So to give you, there are other observatories that are also using AO technology. When I worked at LBTO, I also worked on AO projects there. So LBTO is a very specially designed telescope. It actually has 2 8.4 meter mirrors that are mounted on one mount, and the telescope operates in some sense like a pair of binoculars, so literally moves as one telescope. So each of these telescopes, each of these primary mirrors, has a secondary mirror that basically captures the light at this prime focus area and then aims the light back down towards the main primary mirror and off to a variety of digital cameras and instruments. So the special thing about these mirrors, for some idea, the deformable mirror at Gemini that was correcting the wavefront, the aberrations in the wavefront, was probably the size of my hand or smaller. These secondary mirrors are almost a meter across, and they are extremely thin shells, and they contain almost 672 actuators. So that's what this image that you see here is, that thin shell with all the actuators. The interesting thing about this is the more actuators you have, the more finely you're able to flex the mirror, the better your correction of the wavefront, the better the correction of the aberrations. So this is an extremely powerful tool. In fact, to give you some idea, when the system is operating, it produces an image quality that's 3 times better than the Hubble Space Telescope, which of course has been a benchmark astronomers for most of astronomy for most of its lifetime. So this is kind of a neat science image that I wanted to share. Every time I see this, it really makes me excited, because the thing about LBT is, even though there are 2 beams of light and 2 separate telescopes, there is a way to combine those beams of light. And when you do that, you are able to get the resolution of a 22.8 meter telescope. So what this means is that LBT was really the first of the next generation of telescopes. It gave us a preview into what we're going to see in the next 10 or 15 or 20 years in our field. And so this is a ground-based resolved image of a volcano on Io, okay? And Io, of course, is a moon of Jupiter. So you are actually looking at this bright spot is the image of a volcano on another moon of another planet. And that's how good we can now do from the ground with this kind of system. Okay, but so far we've been talking about a lot of bigger telescopes and some of the technologies that go on those telescopes. But bigger isn't always better. Sometimes what you really need is precision. So here at Kitt Peak, we are actually discovering new worlds with precision at the WIN 3.5 meter telescope. And why is this important? Well, the science that we do with this level of precision is incredibly fundamental to the human condition. We have always asked the question, are we alone? Are we alone in this universe? And one of the main ways of answering that question is to find Earth-like planets in the habitable zones of their parent stars. In other words, we're looking for Earth-sized planets that could have liquid water and therefore could have life. And this is obviously a priority goal of the astronomy community and probably all of humanity. One of the ways that we find these planets is to look for the signatures of their gravitational pools. Those gravitational pools produce signatures of the spectra of their host stars. So very simply put, a star that has no planets, its center of mass is its center, and when it rotates about that center. Any star that has a planet, the system itself will have a different center of mass that will not be the center of the star and causes a wobble in the star as it rotates. We can detect that wobble. And so we build extremely precise instruments, and these require tight pressures and temperatures and specially controlled rooms that people don't even enter to be able to give us the precision to detect this very small signature in the star's wobble, basically in the star's spectrum. The other part of this that's important, and the reason why a telescope like WIN can capitalize on this technology, is it requires a cadence. That means you must be observing this object fairly regularly. And so with larger telescopes that are oversubscribed, many people wanting to use every night, it's very difficult to get these kinds of observations. But at WIN, where over 70% of the time of the telescope is dedicated to this project, you're able to get these cadences that are able to get the precisions that we need to find these Earth-like planets. So at WIN, we're very fortunate to be hosting an instrument that's called NUID that does this type of work. NUID is an extreme precision radio velocity spectrograph that's designed with about a 30 centimeter per second RV precision. Just as a comparison, the Earth has about an 8 centimeter per second RV. It gives the sun that wobble. So we wouldn't see quite an Earth-sized planet, but very, very close. It is funded through a great partnership with NSF and NASA called NN Explore. And through that, it's fully supported with Q scheduling, which means that we can do the cadence to get the precision we need. It has a state-of-the-art data pipeline, which means that anyone, you don't have to be an expert in EPRVs to use this instrument, and a NASA-funded data archive. Kitt Peak resides on the land that belongs to the Tono Ohotom Nation. We are actually within the nation's borders. And so in order to honor our relationship with the Ohotom people, Nid was named, and it is a word in the Ohotom language that means to see or to visualize. And so we have just finished our first full semester of science operations, and we already have some amazing and great results where we've been able to characterize the physics of some of these extrasolar planets. So we're not just finding the planets, we're actually doing physics with them now. Okay, so I think we're doing pretty well on time. I wanted to talk a little bit about what the control room of a state-of-the-art telescope looks like. And instead of just talking to you about it, I thought that I would show you. And so, hold on for just one moment here. So I am actually coming to you today from the control room of the WIN 3.5 meter telescope. And so I'm going to try really hard to take you on a little journey around the telescope to do kind of a virtual visit. Now, I admit, and I will warn you, that our telescope, we have poor Wi-Fi signal here. And the reason is that we have radio observatories also on the property. So our Wi-Fi is actually very weak. So we are going to do our best to take this adventure together. And so I hope you'll have some patience with me while I try to hopefully show you through the control room and show you the new and clean room and hopefully the telescope. And so I guess we're going to take, first I'll show you the control room here. This is Chris, one of our staff members who very hopefully will be helping us. And he is sitting at what we call the TO station or the OA station. So this is actually where the telescope is controlled every night. And so basically, you'll notice that there are several monitors actually. You need a lot of monitors because you're looking at a lot of data, a lot of information about the position of the telescope, all of the safety systems of the telescope. And so really there's a lot to keep track of every night to make sure the telescope is safe. You also have to look at the weather conditions for the summit. So it really requires a lot. Here we're actually panning through the control room and you'll see me there. This is where we would actually control the instruments. So those special cameras that I was talking about during my talk. Okay, I'm going to pause my video here while we try to move. So Martina, I don't know if there are any questions that I could answer while we are trying to shift locations. I can't hear, of course, because you're muted, I think.
Hi, can you hear me, Michelle?
Hi. Hi, I am Roser. I am a first year student. So I wanted to ask you as a student of that's just starting, when you face a new problem and an unexpected problem, how do you usually face it in your field as an optics, like, well, that's basically in your field. How do you usually proceed when you face an unexpected problem? I don't know if I explain myself.
I'm so sorry. The audio is very garbled through the microphone. Can you maybe try to repeat your question now that everyone's heard it? Can you repeat your question just to me?
Yes.
Not through the microphone?
No, I don't know how can maybe I can write it somewhere.
Or just not use the microphone?
Do you hear me now, like this?
Yes, I do. Yes.
Okay. So I'm a first year student, so I was curious as how do you face an unexpected problem in this specific field that it's complicated, that how do you analyze and face the problem, and that's it.
No, it's okay. Well, so a lot of our problems, some of our problems are day-to-day problems, and you have to have very quick solutions. And so with that, often you'll be working, on your knowledge that you have and with a team of people who are experts. So there are many problems that, in the moment, telescope time is very precious. So you have to try to fix those problems very quickly. But there are other problems that are like the challenges I was talking about in the field that literally take decades to fix, to figure out and understand. And usually those problems are fixed through technology. So this is where astronomers work with engineers and opticians to come up with novel problems. So the first step is figuring out the scale of your problem. Is it a day-to-day problem, something that can be solved in months or years, or a problem that takes decades? And then from there, you'll understand the best way to approach it and who to get help from, because a lot of it is getting help. I don't know if that makes sense.
Yes. And I have another question.
Okay.
So what are the requirements that a material needs to be used as a receptor on the telescope? Is it necessary to have certain properties to be a good material to
Yeah.
be used in a telescope?
Yeah, no, that's a great question. So it depends on the use of the object. So many of our cameras are cryogenic, which means they are at very cold temperatures. And that means that you have a kind of interesting challenge because you're heating and cooling the instrument down multiple times. So for instance, if you have materials that don't contract and expand together, your instrument might not work. So gears may grind, for instance, or the optical surfaces, the properties of those surfaces may change. So for instance, using materials that are homogeneous or that have the same rates of contraction and expansion is very important. A lot of mirrors are actually made of very special glass. It is a specialized glass that's melted down in ovens and then formed into mirrors and then coated with things like aluminum or silver. So it's actually, our material science is very important in this field, both for the ability to control temperature and the optical properties. I'm going to try and turn my camera back on, hopefully.
Well, thank you very much.
Hopefully we will see. Okay, so now we are in one of the rooms in the building. And here in front of you, you'll see this room here. And inside this room is actually where NUID, that very special spectrograph looking for Earth-like planets, this is where it's kept. And unfortunately, we can't go in the room. As I said, it's very carefully temperature controlled, but this gives you a sense that the instrument is actually inside an entire room, and it is fiber fed from the telescope itself. So I'm going to leave my camera on and try very carefully to go up the stairs. And thank you for joining me on this adventure. I hope my internet connection stays solid, but if I can make it up here, it'll be a treat. Does anyone have any questions?
Any more questions? Michelle? Michelle, can you hear me?
Hello?
You're okay. Hi.
Can you hear me?
We can.
Can you hear me?
Yeah, but it's like.
Yeah.
Yeah. We have a bad connection. Michelle? We're having problems with the connection right now. I don't know if you can hear me. Michelle? Well, I think we lost Michelle.
Recording stopped. Recording in progress.
Michelle?
Oh.
Hi.
So it seems that I can't quite get the connection I want. So I'm going to try to go outside quickly and show you the dome.
Okay.
So I'm sorry about that. I had hoped we would make it.
It's okay.
But not so much. We'll see. Okay. I can't get up there. I can't get up there. Okay, we'll try one more view. This is the dome of the WIN 3.5 meter telescope. Can you all see it?
Yes, we can. Michelle, we're having problems again with the connection.
Here.
We can hear you right now.
So this is 9 meter.
Michelle? Michelle?
Recording in progress.
Okay. I think that's probably it for the video. Sorry about that. We did the best we could.
Yeah, it's okay, no problem. So,
Does anyone have any other questions, though?
yeah, I have one question. First, I wanted to congratulate you for the amazing talk. And then, can you talk a bit more about the movement system in the adaptive optics devices, please?
Can I talk about the, sorry, say again?
The movement system in the adaptive optics devices. I don't.
Oh, the system. Okay.
Yeah.
Yes. You said the moving system?
Yeah, the movement system. Yeah. Yeah.
Okay. So basically, the way that adaptive optics devices work is that, again, you have a kind of passive wavefront sensor. Obviously, it's ingesting and taking data, and it's looking for deformations in the wavefront. And so it's basically doing that. There's several ways to do that, but basically, often what you'll have is a lens-lit array or something that takes the light and divides it and then looks at the differences through this lens-lit array. And so that's usually a device. There's a very large computing system that backs these kinds of devices. Basically, it does fairly complicated mathematics based upon optical aberrations. I don't know if any of you have heard of the Zernike polynomials, or but basically what it does is it figures out what is happening with that wavefront, what is creating the error. So you may have heard terms like coma or astigmatism, but there are many different types of distortions that might be caused by the atmosphere. The deformable mirrors themselves are exactly what they sound like. They are mirrors that have actuators on the back, no matter how small or large. They have some way to literally change the shape of the mirror to mimic the shape of the wavefront. And so once the aberration is calculated, you're basically taking what is a distortion like coma or astigmatism or tip tilt, and you are transforming it into an actual physical motion, which we would call a slope on the deformable mirrors themselves. And then really what you end up doing is you end up doing twice the opposite of the aberration, and that's what actually flattens the wave. And then that wave is just fed into any instrument that you like, usually near-infrared instruments. So again, this is an iterative process. You don't just measure one wavefront and then you're good to go. You have to constantly measuring wavefronts and sending corrections to your deformable mirror, which can happen up to 1,000 hertz. So it's a very fast process. So these mirrors, the actuators need to be able to respond very quickly. And the ability of the actuators to respond and how much they can change the wavefront tells you how good your system is likely to be. I don't know if that answers your question or gives you some idea.
Yeah, thank you. And does anyone have any questions? Well, I actually had one more question, and it is that, there are a lot of people here that are undergrad students that it's our first year studying physics. So, is there any advice that you could give us to, I don't know, like this career?
Yeah, I think if you'd like, it depends on what you'd like to be. If you'd like to be an astronomer, obviously, you are going to have to go on and probably get a graduate degree. However, there are especially lots of jobs at observatories that do not require a PhD. There are a lot of ways to be involved in astronomy with a bachelor's or master's degree. And so many of the people who operate the telescopes nightly or take images with the cameras, really a lot of them are people who completed a bachelor's or a master's and just have a real passion, not only for telescopes, but for serving the community, because that's really what we're up here doing. We're often nightly taking data for astronomers around the world. And so you really have to have a passion for that, and it's a lot of long nights. So what I would mostly recommend is if you have the chance, if you're interested in a field at an observatory, a job at an observatory, is to try to observe. Find telescopes that are looking for operators where you are, or volunteer. A lot of times they're looking for people to help them take data, volunteer to go with a professor or with someone doing research, to go on an observing run. Figure out whether you're interested in telescopes and tools of astronomy. If you have a chance to participate in an instrumentation project of any kind, that is usually a huge boon when looking for a job in this field. So I would say a lot of this is about creating opportunities for yourself to prove that you have an interest in the optics, in the instruments, and in the observatories, and that you're interested in doing the service.
Okay, thank you, Michelle. And we have one more
No
question
problem.
in YouTube. So Paola Vargas says, does the position of the telescope influence the capture of images of space? And in turning the design of the telescope, is possible to take the telescope from the Canary Islands to Chile and work?
No, that's okay. Okay, so the first part, the telescope is able, unfortunately we weren't able to see it, but the telescope is obviously able to move so that it can point to any area of the sky or most areas of the sky. So maybe I'm misunderstanding the question, but obviously like where the telescope was pointed is the part of the sky that it's seeing at that moment. But you know, the telescopes in the northern hemisphere are only able to see the northern part of the sky, and in the southern hemisphere they see the southern part of the sky. And the sky is different because, of course, as the Earth goes around the sun, and it has a slight tilt to it, and as it rotates, obviously during the nighttime when we're faced away from the sun, the way that you're pointed, you're looking into a different part of space. And if you're pointed to the north, you're looking kind of what we call the northern hemisphere, the northern constellations, or the southern constellations. There's obviously overlap, but this is why, for instance, people in the north can see the North Star and people in the southern hemisphere can't. So where the telescope is located does make a difference in what you observe. However, I will say that for the most part, we know that our sky is what we would call, the universe is uniform and isotropic, which means that there's kind of interesting things no matter where you point your telescope, so it's not like you're ever out of an object to look at. However, and it's an interesting question about the telescopes in the north and the south. An observatory like Gemini Observatory, which is where I did my postdoctoral fellow, actually has two identical telescopes. One that is in the northern hemisphere in Hawaii, and one that is in the southern hemisphere in Chile. And a lot of telescopes are paired in this way. So for here, instance, our telescope, Kitt Peak National Observatory, has a sister observatory in Chile called Cerro Inter-American Observatory. And both telescopes have near identical 4-meter telescopes that were built, well, many years ago now. But basically at the time state of the art in both hemispheres. And so this allows us to kind of look for interesting things whether you're in the north or the south. So I hope that answers the question. I hope I understood the question.
Okay. We have one more question from Jorge from YouTube. And he says, does these large telescopes have a limit on the short distance? Is there a minimum distance that it can be observed? And thanks for the talk.
Sorry, can you say that again? A minimum?
Yeah, sorry. Do these large telescopes have a limit on the short distance? Is there a minimum distance that it can be observed? Thanks for the talk.
I'm not sure I understand. I'm not sure I understand about minimum. Oh, minimum distance. Like, okay, so yeah, that's a good way to phrase it. So I would say.
Michelle, can you hear me?
Yes.
They are asking about the range that you can observe from the same telescope. You can observe a very large distance, but which is the range
how near you can observe with the same telescope. If you can go
Yeah.
from 13 billion years, and then how next
I-
to you.
Yeah, that's actually a really hard question because the telescopes themselves, each individual instrument has its own limits. And what that instrument does determines those limits. So for instance, with a spectrograph, because you're taking a point of light and you're separating it until its entire spectrum, if an object is very faint, it's hard to do that because you're spreading just the same light out over a larger area. And so spectrographs generally have to operate on brighter objects, or they can't see as faint as you might see with the same telescope with an imager, where all the light is condensed into, you know, that very small disk. So it's a really hard question to answer. I will say this, I know when I was at Gemini Observatory, you know, we were able to see very distant objects, you know, that are billions of light years away. But I do also know that we did work in our own solar system. So for instance, I worked on a project where we were looking at superbolides, which are like giant impactors that impacted the surface of Jupiter. And obviously, as you saw, the LBT was able to look at the moon of Jupiter, Io. So really, the largest telescopes with the correct instruments and the correct setups can see things in our own solar system, can see comets and asteroids and planets. But they can also look, you know, billions and billions of years away. So I would say there's the only real limitation is probably your imagination and whatever technology, you know, we can come up with to make it happen. I will say that there is a limit in terms of distance. So understand too that we talked about the electromagnetic spectrum. And so as things are further away, and this is kind of a little complicated, the light that we see from them is redshifted. And what that means is that light that may have been emitted in the optical will actually go to redder wavelengths, and that means different parts of the electromagnetic spectrum. So there's light that shifts so far that we can't actually see it from ground-based telescopes because it's no longer in the optical. So there are objects that are just so far away that basically the light that they emitted has changed character, and we can't detect it with optical and infrared. It can't make it to the ground. So I hope that kind of helps. It's a hard question, actually. It's a good question.
Okay, we have another question from Luis Carlos García Moreno. How are the mirrors of the National Observatory telescope collimated? Thank you.
How are they collimated? I'm trying to think of. Okay, so collimation. What we call collimation is a slightly different thing than I think a lot of people with, you know, small telescopes. They will physically, although I guess it is kind of the same thing, they will physically stick their hand in and they will move like the secondary mirror of like a small telescope, like a Meade telescope or like some small telescope, or even 12-inch, 16-inch is generally how you do it. We don't have the capability to, you know, literally kind of move our secondary in that way, but we can do some movements. So collimation is really just aligning the optical paths, right? And so there's just a variety of ways that we can do that. We have a variety of actuators that can move all of the different mirrors, adjust them slightly. And so it's not just a matter of moving like one secondary mirror, but it's really like moving the optical path of the entire system. And also like we will often call collimation anything that we do to improve the image quality. And that can happen with actuators at the back of the primary mirror that can actually adjust for the gravity vectors as these giant mirrors move. The effects of gravity on the primary mirror changes the shape of the mirror, and we need to change it back. So, you know, if you think about collimation in terms of just aligning the entire optical light path, we have a lot of ways to do that on any big telescope. And we have a lot of feedback from data from bright stars that kind of tells us, okay, you know, are our optics aligned?
Okay, thank you. And does anyone have any more questions? Okay.
Hi.
Hi.
I want to question that for your vital experience, yes, of living in different parts of the world, because if you work in a laboratory, it's a university have one, but if you work in an observatory, you have to work to a specific part in the world, and I want to know if what is this experience for you, and if you recommend it?
I loved traveling, and so to be honest, so I was the first person in my family to go away to college of any kind. Certainly the first to get a PhD, and I grew up kind of with interest in the world, but like my family really didn't travel much, and you know the United States is very large, so traveling outside the country is not as common as it is here in you know as it is in Europe and other parts of the world. So for me, when I became an astronomer and I started going to conferences, and then I started traveling to take my own data. So I went to Chile to take a lot of my graduate thesis data, and then started traveling to many other places, including Europe and South Africa. I just had a passion for it. And so when the opportunity came, I knew that I wanted to do instrumentation. So I knew I wanted to work with big instruments. Which I could have done anywhere, right? Like I actually had a job offer in Germany, so I could have gone there, but there are many places in the US I could have stayed closer to home. But when the opportunity came at Gemini, I was passionate about telescopes, and I thought it would be amazing, and it was. I loved living in La Serena. Embarrassingly, it's been 10 years since I lived there, so my Spanish is terrible, and Martina knows. But basically, for me, it was part of the fun. To learn. And also what I found is with astronomy, we talked about all these challenges that you face with the astronomy, with the research, and coming up with new technologies. And I find that there's a global approach to those solutions. There are, you know, people all across the world, they have different ways of problem solving, different ways of thinking. And when you become a global citizen of the world and you start interacting with all those different people in academia, you find that you come to your problems faster. This is why diversity is so important, because many different brains come up with a very unique answer. And so that's been a passion of living abroad and experiencing different cultures and working with different people in a diverse atmosphere. It really can't. I love it. I would never change it. And I love living in Arizona. You know, I'm back home in the U.S., but I'm from New Jersey. So for me, Arizona is away from home, you know. But I love living here, and it's been a real gift the last 10 years.
Okay.
So yeah.
Thank you. So sounds nice. Yes.
It is nice.
Okay, Michelle, so I think that we have no more questions. So
Okay.
Thank you for being here, and it was an amazing talk, so thank you so much.
Oh, great. Okay. Well, thank you very much to everyone, and good luck with your studies. And as the summer is heading, I hope that you have good finals and then have a great summer vacation and do something good and prosperous for your career and for your lives.
Thank you. Bye.
Recording stopped.